Hello, welcome to the next lecture on signals and systems. And in this lecture, we will be covering some example questions for classification of systems. So, in the last lecture, we discussed regarding what basically a system is, and the different classification, or let's say different properties of that a system can hold. And when we were discussing what a system was, what we were basically doing is we defined a system as something that takes in an input, does some process to the input and gives it as an output. But one of the major thing was that we should be able to represent the system as a mathematical equation. Okay, so now let's now keeping that in mind, now let's right away jump into a set of questions. So the first one is determine whether the following systems are linear and time invariant. That is, we have to check for linearity and we have to check for time invariance. Okay, so the first one is y of t is equal to log x of t. We may have seen one or two of these in the last lecture, but anyway, let's solve them completely. Okay. Minus infinity to infinity x of tau e to the power of j omega tau d tau. Okay, so let's consider them one by one. Let's consider the first one, a, that is y of t is equal to log of x of t. Okay, so first we have to check for linearity, right? So what is the condition for linearity? If you remember, x1 t plus x2 t should give, what should it give? It should give y1 t plus y2 t. In fact, a x1 t plus b x2 t should give a y1 t plus b y2 t. Superposition should be followed. But here you can directly right away see that y1 of t is equal to log x1 of t and y2 of t is equal to log x2 of t. But y1 of t plus y2 of t, it is equal to, it is right, it is not equal to what? Log of x1 of t plus log of x2 of t. It is not equal to, right? Because how will we get this one? You will have to write, to get this one, this is log of x1 of t into x2 of t. This is equal. That is not the input that we are expecting. So anyway, this is not equal the same, and therefore this is non-linear. Okay, now let's check for time invariance. So first we are shifting the input, so y1 of t is equal to log of x of t minus t naught. Okay, so now here if we shift the whole thing, y of t minus t naught. How will we get y of t minus t naught? That is, we have to completely shift everything in the input, right, on the right side, that is t minus t naught. Both of these are the same, therefore this is time invariant. So this system, this particular system, it is non-linear but also time invariant. So let's see the next one, B. What was it? It was y of t is equal to e to the power of t xt. Okay. So how do we check for linearity? y1 of t is equal to e to the power x1 of t, and y2 of t is equal to e to the power of t x2 of t. Now if we give the input as if we give the input as what, x1 of t plus x2 of t, what will be the output? Let's denote it as y of 3. Then what is the output? E to the power of t x1 of t plus x2 of t, which is not equal to e to the power of t x1 of t plus e to the power of t x2 of t. Therefore this is non-linear. Okay. How do we check for time invariance? First we see what the output for a shifted input. It is e t x t minus t naught. Okay. Now what will be the result? What will how will we get a shifted output? We have to shift all the time terms in the right side, right? So it will be e t minus t naught into x of t minus t naught, both of which are not obviously the same. Therefore it is time variant. Okay. So this system, yt equal to t e to the power of t xt, it is at the same time non-linear and it is also time variant. The next question was y of t is equal to integral minus infinity to t x phi tau d tau. Okay. So for linearity, how do we check? We take y1 of t is equal to minus infinity to t x1 of phi tau d tau, and y2 of t is equal to minus infinity to t, right, x2 phi tau d tau. Let's add two variables also. Let's call it a1 and a2. Okay. Now what is the result? What is the output if we give a1 x1 t and a2 plus a2 x2 t as the input? y3 is equal to integral minus infinity to t a1 x1 of phi tau plus a2 x2 of phi tau dt, sorry, t tau, which is equal to y1 plus y1 of t plus y2 of t. Therefore this is a linear system. Now let's check for time variance or time invariance, whichever is it. Okay. So if you are shifting the input, y1 of t is equal to minus infinity to t x of phi tau minus t0 dt d tau. So since we are adding a shift, to an already existing function, we have to change the variable of integration into a new one to take into account this shift, right? So what do? We put phi t minus t2 equal to lambda, and we differentiate both sides, so we get phi d2 is equal to d lambda, implies d2 is equal to d lambda by phi. So we can replace lambda here, but we also have to see how the limits change when we are changing the variable of integration. Okay, so as t tends to minus infinity, how does lambda tend? Lambda also tends to minus infinity. Okay, and as t tends to tau tends to t, what does lambda do? Lambda equal to phi tau minus t0, right? So what happens? Lambda is equal to phi t minus t0. So if we replace this in the original equation, what will it be? It will be y1 of t is equal to minus infinity to phi t minus t0. Okay, phi t minus t0 into x of lambda d lambda by phi. We can take the d lambda outside, so it will be something like 1 by 5. Let me just write it here, 1 by 5 minus integral minus infinity to phi t minus t0 x of lambda d lambda. Now in this equation, if we shift the whole thing by t0, right, if we replace t by t0, the whole thing, it will be, what will be? Y of t minus t0 is equal to minus integral minus infinity to t minus t0 x of phi tau d tau. Right, here we cannot put it as phi tau minus t0, because the variable we are considering is t only, right? So we can only change t. Now obviously these two are not the same equation. That is the system response we get when we are shifting the input, and the system response we get when we are shifting or the system input which is required to get a shifted output are not the same. Therefore this system is time variant. And so this is a linear time variant system. Okay, and the last one was, what was the last one? It was y of t is equal to e to the power of minus j omega t minus infinity to infinity x of tau e to the power of minus j omega tau d tau, right? So again y1 of t is equal to e to the minus j omega t minus infinity to infinity x1 tau e to the power of minus j omega tau d tau, and y2 of t is equal to e to the power of minus j omega t integral minus infinity to infinity x2 of tau e to the power of minus j omega tau d tau. Now what is the response if we give the input as x1 of t plus x2 of t? Y3 of t is equal to integral minus j omega t minus infinity to infinity x1 tau plus x2 tau into e to the power minus j omega tau d tau, which is equal to y1 of t plus y2 of t. Therefore this is a linear system. Okay, now let's check for time variance or time invariance. So here also, like the last time, we need to change the variable as we are introducing a shift in the input. So y1 of t minus t0, sorry, y1 of t is equal to e to the power of minus j omega t integral minus infinity to infinity x of t minus t0 e to the power of minus j omega 2 d 2. Okay, so when we are changing the variable t minus t0 equal to lambda, and implies d 2 equal to d lambda, and also what is it, 2 is equal to lambda plus t0, and since tau minus t0 equal to lambda, as tau tends to infinity, lambda also tends to infinity, and as tau tends to minus infinity, lambda will also tend to minus infinity. So this, when we substitute here, what will this be? Will be e to the power of minus e to the power of minus j omega t minus infinity to infinity, right, x of lambda e to the power of minus j omega lambda plus t0 d lambda. Okay, let's call it equation 1. Now we want to see what is the total response of the system if the output is to be shifted by an amount t0, right? Then it means the whole thing on the right side should be shifted. So it will be e to the power of minus j omega t minus t0 integral minus infinity to infinity x of tau, right, x of tau e to the power of minus j tau d tau, right. Obviously these two are not the same, therefore this is time variant. Okay, so this is how you check for linearity and time variance of different systems. So there might come a question like check if the system is an LTI system or not, that is whether the system is linear, time invariant, right? So what do you do? First you check for linearity separately and you check for time invariance separately. So only a system is LTI only if it is both linear and time invariant. Okay, so that was regarding linearity and time invariance. An easy method for looking for linearity is that basically what is linearity? Linearity means that the response, system response should be a straight line, right? It can be a straight line of any orientation, starting or ending at any point, but the thing is that it should be straight line at the region where we are considering the system. So that might be helpful. So whenever you are asked to check if system is linear or not, you can straight away, sometimes you can you can just straight away understand that okay, certain systems are non-linear, like trigonometric functions are directly non-linear, logarithmic functions, exponential functions, these are all non-linear because their response will be different, right? trigonometric, logarithmic, whatever, exponential, those will be different. So you can right away, even without checking some functions, if you know the proper response of this mathematical function, right away you can see whether it is linear or not. Okay, now let's see some questions regarding the other properties of systems. Here in this, for these questions we'll be testing for all the properties, but that linearity and time invariance it was given separately because LTI is sort of important, and that may be asked separately. So here the question is, find whether the following systems are memoryless, invertible, causal, stable, time invariant, and linear. So right away, like from this statement itself, you can sort of understand that these are the properties of a, or the desirable properties of a system for us to work with. That is, it is LTI, linear time invariant. It should be stable, should be causal, it should be invertible, and it should be memoryless. These are the actual desirable features or properties of a system. Okay, so I'll just write down one by one questions. Okay, so the first one is y of n is equal to sine of x of n, sine of x of n by x of n. Okay, so how do we so first of all, it is a trigonometric term, right? Trigonometric term, so it is non-linear, but some portions of the system of this will be linear, in the sense that sine theta by theta tends to 1 when theta tends to 0. So the regions close to 0, that is at regions close to x of n equal to 0, this will be slightly linear, but overall it is not linear, non-linear. Okay, then let's see for time. So this is non-linear. Let's see for time variance. So if you are giving the shift in input, it will be something like this, right? And if you want the output to be shifted, what should be the function, right? So that is y1 of n equal to y of, which implies this is time invariant, right? So we checked two properties. So here if you see, y of n is equal to sine of x of n by x of n, right? That is the system at any given point of time, it depends only on the present input, that it doesn't depend on the past or future inputs, right? So there is no x of n minus something or n plus something, only x of n. Therefore this is both memoryless and causal, right? Then what are we looking for? What else is there? There is the invertibility and stability conditions, right? So what was the condition for invertibility? Invertibility condition was for every there should be a unique input for every output. That is the condition for invertibility. So suppose I am taking xn as n, then what is, let's say y1 of n is equal to sine n by n, right? What if I take x of n as minus n, then this is equal to sine of minus n by minus n, which is again sine of n by n. That is, two different inputs are giving the same output, therefore it is not invertible. It is non-invertible. Okay. And the last one, stability. Stability, the function is sine of x n by x of n, right? So here sine of xn is finite for finite x of n, implies y of n is equal to finite by finite. That is, if x of n is finite, sine of x of n is also finite. So for a finite input, the output term is something finite term by some other finite term, which is obviously finite, right? Therefore this is a this is a stable system. Okay. Now moving on to the next question. Okay, consider the system as y of n is equal to 3 x of n when x of n is less than 0 and 0 and 0 for x of n greater than or equal to 0, right? So this may look like a linear system because we are having a 3 into x of n, but we have to see for what values it is, right? That is, it is x of n, 3x of n for x of n less than 0 and 0 for x of n greater than or equal to 0, right? So it is not exactly linear, right? It is not like so if it was just 3x of n, it would have been linear, but since this is this condition is coming, we cannot say that let's say x1 of n plus x2 of n directly gives y1 of n plus y2 of n for all x1 of n and x2 of n, right? We cannot say, and this is sort of piecewise linear, so this is not linear, this is non-linear, right? But it is anyway, whatever shift we are giving at the input will directly reflect as a shift in the output, so it is time invariant. Okay. The other things we have to look is for causality and memoryless. So there is no n minus something or n plus something. That is, the input is the output is depending on only on the current value of the input. Therefore, let me write it down. Output depends only on the current value of input. Therefore, it is causal and memoryless. Right. Also, what is the thing? It is what is happening for finite values of the input. It is having the input is just multiplied by 3, or it is 0. That is, if the input is finite, the output also is finite. Therefore, the system is also stable. Right. So it is causal, memoryless, stable, time invariant, and non-linear. Right. So some problems will be like this. We may not need to analyze it mathematically much, but some problems we may have to do some analysis. So it depends on the particular question. So moving on to the next one. The system is y of t is equal to integral t to t plus 1. Let me just write it properly. Y of t is equal to integral t to t plus 1 x of tau minus alpha d tau. Okay, alpha is a constant. Alpha is a constant. Okay. So first of all, like I hope you remember, like I said, like some functions you can right away say without analyzing the linearity, right? Linearity or non-linearity that of. And one type of such a function is integration. Integration is always linear. So here you can say it is linear. You don't have to analyze for the linearity of a integral signal. If it is, that is, if it is just an integral. If there is some other term, for example, if it was something into integral of this, then you have to check for the linearity in the proper way. Otherwise, if it is just an integration, you don't have to check. You can right away write, okay, it is linear. Okay, because integration. Right. Now let's see for the time variance part. Okay. So how will it look if the input is shifted? Y1 of t is equal to integral t to t plus 1 x of tau minus alpha minus t0 d tau. So again, like last time, we have to adjust the variable of integration. So it will be, so I am taking tau minus tau 0 equal to lambda. I am not considering alpha because alpha is a shift which is already present in the definition of the system, so we don't have to care for that. Okay, we'll just take the variable of integration and the shift we are introducing, only that too we'll be touching. So from this we have dou tau d tau equal to d lambda, and as tau equal to t, lambda equal to t minus t0, and as tau equal to t plus 1, lambda equal to t plus 1 minus t0. So this when we substitute this back into the equation, we have y1 of t is equal to t minus t0 to integral t minus t0 to t plus 1 minus t0 x of lambda minus alpha d lambda. Let's be our equation 1, and to get a shifted input, what is it? Y of t minus t0 is equal to t minus t0 to t minus t0 plus 1 x of tau minus alpha d tau. You can see the first and the second equations are the same, that is y1 of t is equal to y of t minus t0, which implies what? Which implies time invariance. So this is time invariant. So we have linearity and time invariance. So right away, this is an LTI system, right? This is an LTI system. So next, what we will look for is whether the system is dynamic or not. Okay, that is whether it has some sort of memory or not. Okay, so again let's rearrange the variables a little bit. Okay, this is our original system. So let's rearrange the variable, or let's change the variable the similar way like we did last time. Okay, so t equal to tau equal to t implies lambda equal to t minus alpha, and t equal to t plus 1 implies lambda equal to t plus 1 minus alpha. So what is the difference between how we change the variable in this part and how we change the variable here? Here actually we introduce, that is when we check for time invariance, we introduced an additional shift, that is of t0, and then we change the variable so as to see how tau minus t0 is changing. But here what we are doing is we are not giving any additional shift. We are taking into consideration the current shift itself, right? And then we are converting it into a new variable. Okay, so we have this. So what will our system be? Y of t is equal to integral t minus alpha to t plus 1 minus alpha x of lambda d lambda. So you can see here after the integration we are giving the time values, right? So here we are having what? T minus alpha and t plus 1 minus alpha. That is the output depends on, so this will be what? Integral this will be the integral of first integral of x of lambda, which is given the value that is, it will be first integral of x of t plus 1 minus lambda minus first integral of x of t minus alpha. So what is happening? That is the output is depending on the future or past values of the input, depending on the value of alpha, right? It may be some future value or may be some past value. Either way, it is not depending only on the present value. Therefore, that is, it is output depends on past or future values of input. Therefore, this is a dynamic or memory system. Okay. And how do we check for causality? How do we check for causality? So we'll be taking from here, that is y of t is equal to integral t minus alpha to t plus 1 minus alpha x of lambda d lambda, right? Because our consideration is the same here, right? So for causality, it should depend only on the present and pass values. So anyway, the system here, the output depends on present or past values. It is a memory system, so it is established. So we need to see whether it is causal or non-causal. Here, if you see, we have t minus alpha and t plus 1 minus alpha. So here, if lambda is greater than or equal to 1, what happens? Sorry, alpha is greater than or equal to 1. What do we have? We have integral from t minus 1 to t. If it is 2, if alpha is 2, then what happens? We have integral from t minus 2 to t minus 1. Alright, that is, if alpha is greater than or equal to 1, then the output is depending only on past values of the input. Therefore, for lambda is greater than or equal to 1, the system is causal. Otherwise, it is not causal. It is non-causal, in the sense it depends on future values also. So that is the causality part. So what is the next part? It is whether if the system is invertible or not, right? How do we do that? Okay, regarding the invertibility, this is basically an integrator of a shifted input, right? So integration by itself is an invertible operation, because we have a definite we have an inverse operation for it, right, which is differentiation. So because there are no additional terms added to the or multiplied to the input in this particular system, you can say that it is invertible. If you want to challenge the invertibility of this, you will have to find two values of x of n which give the same y of n or y of t. Then you can say, okay, this is not invertible. Otherwise, it is invertible as it is a integral or integrator. Okay. So that is regarding this particular question. Now let's see one more, last one. The system is y of t is equal to 3x of 3t plus 3. Okay. Okay. So here, regarding the linearity, you can see that this is basically there are no non-linear terms, right? That is, it is just the input is being shifted and time scaled a little bit, and that is it. So the response will be linear. There is no non-linear term, so it is linear. Okay. And time variance, so the shifted output for the shifted input is right, 3 into x of 3t plus 3 minus 3 t0. Okay. And what about the shifted output? To get the shifted output, what we have to do? We have to shift the whole thing, right? Which is equal to 3t plus 3 minus 3t0, which is not equal to y1 of t. So this is time variant. Okay. And what about the causality and memory part? Here, obviously, this value is depending, that is the output is depending on some future value of the input, right? That is x of 3t plus 3. Suppose if t equal to 0, then output is 3x of 3, right? So it is a dynamic system, and it is also non-causal. Okay, that is output depends on future value of input. Non-causal and dynamic. This memory system. And what about stability? Here the output is just 3 into multiplied 3 into the shifted value of the input, right? So if the values of the input are finite, then output is also finite. That is, we have the Biot condition is satisfied. Therefore, this is a stable system. And what about the invertibility? Again, this is what is it? How will the response be? This is the output is basically the input shifted and scaled in both time and amplitude by a little bit, right? So basically, for distinct input, you will get distinct output. Therefore, it is invertible. Or if you want to contradict that, you have to give some. You will have to find some particular two sets of input which gives the same output. Or conversely, you can check the invertibility. The exams to prove the invertibility, you can just give take two inputs. For example, that x1 of t is equal to say u of t, and x2 of t equal to say minus u of t, and see what is the output. So y of t is what? 3 u of 3t plus 3, and here y of t is equal to minus 3 u of 3t plus 3. So you can show for us as an example that okay, distinct inputs are giving distinct output, so invertible. So that was regarding some examples for the classification of systems. So I am stopping the lecture here, and I shall give you some practice problems to do as homework. Shall post it in the Google Classroom, and from the next lecture onwards we will start with proper LTI systems, and we will start with the concept of convolution, which is very important, maybe one of the most important concepts in signals and systems, which is convolution. Okay, thank you.